Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the weight of the day settle away from your shoulders. Where in the world are you watching from? A quiet bedroom, where the stars might be visible through your window? A cosy corner where the universe feels both vast and intimately close? Tonight we're going to explore one of the most fundamental limits in all of existence, the speed of light and why nothing with mass can ever reach it. We'll discover what Einstein revealed about the fabric of space and time itself, understand why faster than light travel isn't just technologically difficult, but fundamentally impossible, and contemplate what this cosmic speed limit means for humanity's dreams of exploring the stars. It's a journey that spans from the smallest particles to the largest cosmic distances, from theoretical physics to the practical realities of interstellar travel. But don't worry, this isn't going to be a frustrating lecture about what we cannot do, filled with complex mathematics and disappointing conclusions. Instead, we'll move slowly and carefully through the beautiful physics that governs our universe, taking our time with each concept, building understanding gently. By the end, I think you'll find that this limitation isn't a cosmic cruelty, but rather a profound insight into the elegant structure of reality itself. If you enjoy these calm explorations of the universe's deepest mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for joining me on these journeys through space and time. So settle in, let your shoulders drop, take a slow breath, and let's begin our slow drift through the physics of light, the nature of space-time, and the ultimate cosmic speed limit. There's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold. The universe has been obeying these laws for nearly 14 billion years. We have all the time we need to understand them. Let's begin with something that seems simple, but is actually quite strange. Light always travels at the same speed, no matter who measures it or how fast they're moving. This observation, this seemingly innocent fact, is what unlocked one of the deepest truths about our universe. In the late 1800s, physicists believed they understood light fairly well. They knew it was a wave, something like sound travelling through air or ripples moving across water. And if light was a wave, they reasoned, it must be travelling through some medium, just as sound needs air and water waves need water. They called this hypothetical medium the luminiferous ether, an invisible substance that filled all of space, allowing light to propagate from the stars to our eyes. But there was a problem with this idea, one that Albert Michelson and Edward Morley discovered quite by accident. If Earth was moving through this ether as it orbited the Sun, they thought, then light should appear to travel at different speeds depending on whether we measured it moving with Earth's motion or against it. Imagine you're on a boat moving downstream. If you measure the speed of waves coming from behind you, they should seem slower than waves coming from ahead. The same principle they assumed should apply to light in the ether. So in 1887, Michelson and Morley built an exquisitely sensitive instrument to detect Earth's motion through the ether. They split a beam of light, sent the two halves on perpendicular paths, then recombined them to see if one had travelled faster than the other. The experiment was ingenious, precise, and carefully controlled, and the result was completely unexpected. There was no difference. No matter which direction they measured, no matter how they oriented their apparatus, light always travelled at exactly the same speed. It was as if the universe itself was conspiring to keep light speed constant, unchanging, absolute. The ether, if it existed at all, was undetectable. More disturbing still, the very foundations of physics seemed to be revealing something profoundly strange about the nature of reality. For nearly 2 decades, this result puzzled physicists. Some proposed increasingly complex explanations for why the ether couldn't be detected. Others suggested that perhaps the experiment was flawed, that some unknown factor was masking the effect they expected to see. But the simplest explanation, the one that required completely rethinking our understanding of space and time, was the one that turned out to be correct. Light's constancy wasn't a peculiarity to be explained away. It was a fundamental feature of the universe, a clue that space and time themselves were far stranger than anyone had imagined. And understanding why light always travels at the same speed would require abandoning some of our most basic intuitions about how motion works. Which brings us naturally to consider what happens when we try to apply our everyday understanding of speed to light itself, and why that understanding, so reliable in our daily experience, completely breaks down at cosmic velocities. Albert Einstein was 26 years old in 1905, working as a patent clerk in Bern, Switzerland, when he published a paper that would fundamentally transform our understanding of reality. He titled it, quote, "One though, history would come to know it as the special theory of relativity." Einstein began with a simple premise, what he called a postulate. He proposed that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This wasn't just an assumption of convenience, it was, he argued, a fundamental law of nature, as basic and unbreakable as any principle in physics, and from this single postulate, combined with the principle that the laws of physics should be the same for all observers moving at constant velocity, everything else followed with mathematical inevitability. But accepting that light's speed is constant requires giving up something we take for granted. The idea that time flows at the same rate for everyone, and that space has the same dimensions regardless of how we're moving. Einstein realized that if light's speed is truly constant, then time and space themselves must be flexible, adjustable, relative. They must change depending on how fast you're moving, warping and shifting in just the right way to ensure that everyone measures light at the same speed. Consider two observers, one standing still on Earth and another aboard a spacecraft moving at half the speed of light. Both shine a flashlight forward and measure how fast the light travels. Common sense suggests that the person on the spacecraft should measure the light moving away more slowly, just as a ball thrown forward from a moving car moves faster, relative to the ground, but at normal speed relative to the person throwing it. But that's not what happens with light. Both observers measure exactly the same speed for the light from their flashlights. The person on Earth sees their light travelling at 300,000 kilometers per second. And impossibly, the person on the spacecraft also measures their light travelling at 300,000 kilometers per second, not at a reduced speed as intuition would suggest. This seemed like a contradiction, a violation of basic arithmetic, but it's not. What's actually happening is far more profound. Time itself is running slower aboard the spacecraft. Space itself has contracted in the direction of motion. These aren't illusions or measurement errors. They're real physical effects, consequences of moving at high velocity through the fabric of space-time. The clocks aboard the spacecraft tick more slowly than clocks on Earth, not because there's something wrong with them, but because time itself passes more slowly when you're moving fast. And distances in the direction of travel shrink, not because objects physically compress, but because space itself is different when measured from a moving frame of reference. This realization that space and time are not fixed and absolute but relative and flexible was revolutionary. It meant that the universe was far stranger than Newton had imagined, that the stage upon which physics plays out is itself dynamic, changing with the motion of the observer, and it meant that the speed of light occupied a unique and privileged place in the structure of reality. Light doesn't just happen to travel at 300,000 kilometers per second. That speed, which we call c, is woven into the mathematical fabric of space-time itself. It's the conversion factor between space and time, the cosmic speed limit, the maximum rate at which cause can propagate to effect. And most importantly for our journey tonight, it's a boundary that nothing with mass can ever cross. And this brings us to something equally remarkable. What happens to mass itself as you approach the speed of light, and why this creates an insurmountable barrier? There's an equation that almost everyone has heard of, even if they don't quite understand what it means. E equals mc squared. Energy equals mass times the speed of light squared. This simple relationship, also from Einstein's miracle year of 1905, reveals a deep connection between mass and energy. They're not separate things, but different manifestations of the same underlying reality. What this equation tells us, among many other things, is that mass is a form of stored energy. An enormous amount of energy, in fact, because the speed of light squared is such a staggeringly large number. Even a tiny amount of mass contains tremendous energy. This is why nuclear reactions release so much power. When you convert even a fraction of mass into energy, as happens in the sun or in a nuclear reactor, the results are dramatic. But there's another implication of this mass-energy relationship, one that's crucial for understanding why light speed travel is impossible. As an object with mass moves faster, approaching the speed of light, something remarkable happens. Its energy increases, and because mass and energy are equivalent, this means its effective mass increases as well. The faster you go, the more massive you become. At everyday speeds, this effect is negligibly small. A car driving down the highway gains an infinitesimal amount of mass due to its motion, far too small to measure with any existing instrument. Even at the speeds of spacecraft, thousands of kilometers per hour, the increase in mass is vanishingly tiny. But as you approach the speed of light, this relativistic mass increase becomes dramatic, then extreme, then infinite. Imagine trying to accelerate a spacecraft to light speed. At first, your rockets push against the ship's mass, accelerating it forward according to Newton's laws. But as the ship gets faster, its effective mass increases. This means you need more force to produce the same acceleration. So you burn more fuel, apply more thrust, push harder. The ship continues to speed up, but each increment of velocity requires more energy than the last. By the time you've reached 90% of light speed, the ship's mass has more than doubled. At 99%, it's increased by a factor of 7. At 99.9%, it's more than 22 times its original mass. And as you get closer and closer to light speed, this factor grows without limit, approaching infinity as your velocity approaches c. This creates an impossible situation. To reach light speed, you would need to accelerate infinite mass, and accelerating infinite mass requires infinite energy. Not just a very large amount of energy, not merely more than we have access to with current technology, but literally infinite energy. More energy than exists in the entire universe. It's not a technological limitation, it's a fundamental impossibility, built into the mathematical structure of space-time itself. There's a beautiful symmetry to this. Light itself, photons travelling through space, have no mass at all. They're pure energy, and this masslessness is precisely what allows them to travel at light speed. In fact, they must travel at light speed. They cannot slow down or speed up. For a photon, there is no other velocity. But anything with even the tiniest amount of mass, even a single electron, can never quite reach that speed. It can get arbitrarily close, approaching closer and closer with enough energy, but it can never actually arrive at c. Particle accelerators demonstrate this limitation beautifully. Scientists can accelerate protons to 99.9999999% of the speed of light, nearly a dozen nines after the decimal point. But no matter how much energy they pour into the system, those protons never quite reach light speed. They just get asymptotically closer, their mass growing, the energy required for each additional increment of velocity increasing without bound. This isn't a failure of technology or engineering, it's physics revealing one of its fundamental rules. The speed of light is not a speed that massive objects travel at. It's a boundary, a limit, a cosmic speed beyond which the very concepts of mass and motion break down. And understanding why this limit exists leads us to an even deeper insight. Let's pause here and consider a different angle on this same truth. one that reveals why time itself conspires to prevent light speed travel. We've touched on time dilation, the slowing of time at high velocities, but let's explore what this really means and how it creates another insurmountable barrier to light speed travel. The mathematics of relativity tell us something remarkable. As you approach the speed of light, time doesn't just slow down, it approaches stopping altogether. Imagine you're aboard a spacecraft accelerating toward light speed, and you're watching a clock on Earth through a powerful telescope. At first, the clock appears to tick normally, keeping pace with your own onboard chronometer. But as your velocity increases, Earth's clock seems to slow down. The seconds stretch longer. The minutes take ages to pass. This isn't an optical illusion caused by the Doppler effect, though that plays a role too. This is actual time dilation, a real difference in how fast time flows for you versus someone on Earth. And it works both ways. An observer on Earth watching a clock aboard your spacecraft would see it ticking more slowly than their own clocks. Each of you, from your own perspective, is experiencing time at the normal rate, but you're aging at different speeds relative to each other. As your spacecraft approaches closer to the speed of light, this effect becomes more pronounced. At 99% of light speed, time aboard your ship flows at about 1/7 the rate of time on Earth. For every 7 years that pass on Earth, you experience 1 year. At 99.9%, the ratio becomes even more extreme. Your 1 year equals 22 years on Earth. The mathematical relationship is precise and unforgiving. There's a factor called gamma that describes time dilation, and it depends on your velocity relative to the speed of light. At low speeds, gamma is close to 1, meaning time flows normally. But as you approach light speed, gamma grows larger and larger, racing toward infinity. And when gamma becomes infinite, time dilation becomes complete. Time stops entirely. This is what would happen if you could somehow reach light speed. Your clock would stop ticking. No time would pass for you at all. From your perspective, your journey would take 0 time, regardless of the distance travelled. You would arrive at your destination at the same instant you departed, experiencing no passage of time whatsoever. But here's the paradox. If no time passes for you, then you can't experience anything during the journey. You can't think, can't observe, can't exist in any meaningful sense during the transit. You would be frozen, not in space, but in time itself. And this reveals something profound about the nature of light speed. For a photon, travelling at light speed, this is exactly what happens. In the reference frame of the photon itself, if we could adopt such a perspective, no time passes between emission and absorption. A photon emitted from a star 1,000 light-years away experiences no duration during its millennium-long journey to Earth. From its perspective, it is created and destroyed in the same instant, even though observers watching from outside see it travelling for 1,000 years. This timelessness of light is built into the fabric of the universe. It's why photons can never decay, never change. They exist outside the flow of time as we experience it. But for anything with mass, for anything that experiences the passage of time and can undergo change, this state is unreachable. You cannot freeze time and still exist as a thinking, experiencing being. There's another consequence of approaching light speed that makes the journey not just impossible but meaningless. As your velocity increases, the universe ahead of you appears to contract due to length contraction. Distances shrink in your direction of travel. At 99.9% of light speed, a journey that would normally span 10 light-years would contract to less than half a light-year from your perspective. At light speed itself, this contraction would become total. The entire universe in your direction of travel would shrink to 0 distance. All destinations would be at the same location, right at your current position. Space itself would cease to have meaning. The journey and the arrival would be the same event, separated by 0 distance and 0 time. These aren't just mathematical curiosities. they're revealing something essential about what light speed represents. It's not just fast, it's the speed at which space and time themselves break down, where the familiar concepts of duration and distance cease to apply. It's a boundary beyond which the universe as we know it doesn't exist. Building on this foundation, we can now explore what happens to the very concept of cause and effect when we contemplate faster-than-light travel. Perhaps the most profound reason why faster-than-light travel is impossible has to do with causality itself, the principle that causes precede their effects, that the arrow of time points in one direction. Violating the light speed limit doesn't just mean going very fast, it means breaking the fundamental order of events, allowing effects to occur before their causes. This isn't immediately obvious, so let's explore it carefully. In relativity, events that are separated in space and time have a relationship that depends on the reference frame from which they're observed. For events that are close together in time and far apart in space, different observers moving at different velocities can disagree about which event happened first. Imagine two stars, 10 light-years apart, that explode. The explosions happen, from Earth's perspective, within 1 year of each other. Now, there exist reference frames, observers moving at high velocity, who would measure the explosions in reverse order. What Earth sees as star A exploding first, then star B, some high-speed observer might measure as star B exploding first, then star A. This seems strange, but it's not a problem because the stars are too far apart for their explosions to have caused each other. Light from star A's explosion takes 10 years to reach star B, far longer than the 1 year between explosions, but now imagine you could send a signal faster than light. Suppose you're on Earth and you send an instantaneous message to star B 10 light-years away. From your perspective, the message arrives the instant you send it, but from the perspective of certain high-speed observers, something bizarre happens. They measure the message arriving before it was sent. Effect precedes cause. The message is received in the past relative to when it was transmitted. This isn't a flaw in the mathematics, it's a direct consequence of how space and time work in relativity. Different observers have different definitions of simultaneous, and once you allow faster-than-light signalling, you create situations where causality can be violated. And if you can violate causality, you can construct paradoxes. The classic example is the grandfather paradox, usually discussed in the context of time travel. If you could travel backwards in time and prevent your grandfather from meeting your grandmother, you would prevent your own birth. But if you were never born, who travelled back in time? The paradox resolves only by recognizing that backwards time travel is impossible. But faster-than-light travel creates exactly the same paradoxical situations. Imagine two spaceships moving past each other at high velocity. Ship A sends a faster-than-light message to Ship B. Ship B receives the message and immediately sends a faster-than-light reply back to Ship A. Due to the relativistic effects of their motion, the geometry of space-time allows the reply to arrive at Ship A before the original message was sent. Ship A receives a response to a question it hasn't asked yet. Cause and effect have become untangled. The universe doesn't allow this. The speed of light isn't just the fastest speed at which objects can move, it's the fastest speed at which information can propagate, the maximum velocity for causality itself. It's the cosmic speed limit on cause and effect, ensuring that the universe makes sense, that the arrow of time points consistently in one direction for all observers. Some physicists have proposed exotic solutions to this problem, ways that faster-than-light travel might be possible without violating causality. These proposals often involve warping space-time itself, creating shortcuts through space rather than moving through it. But even these exotic solutions face tremendous obstacles, both theoretical and practical, and they all respect the fundamental rule: you cannot transmit information, cannot cause an effect, faster than light relative to the local structure of space-time. The light speed limit is therefore not just about energy or mass or practical engineering. It's about maintaining the logical consistency of the universe, ensuring that effects follow causes, that the future remains the future and the past remains the past. Break this limit and you don't just travel fast, you shatter the fundamental order of reality, and so we come to understand slowly that light speed isn't a challenge to overcome. It's a foundational principle of how the universe operates, as essential as the laws of thermodynamics or the conservation of energy. Accepting this limit means accepting that the universe is structured in a very particular way, that space and time are not the passive stage upon which events unfold, but active participants in the cosmic drama. This sets the stage for what comes next, understanding not just why we can't reach light speed, but what we can achieve within this cosmic constraint, and what it means for humanity's future among the stars. Let's shift our focus from abstract physics to practical engineering, from Einstein's equations to the harsh realities of rocket propulsion. Even if relativity didn't forbid reaching light speed, even if the speed of light were just a very fast velocity rather than a cosmic boundary, we would still face enormous challenges in achieving it. The fundamental problem is one that rocket engineers confront every day: the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, describes a simple but brutal relationship. To accelerate a spacecraft, you must carry fuel. But fuel has mass, and that mass must also be accelerated. So you need more fuel to accelerate your fuel. But that additional fuel also has mass. You need fuel to accelerate the fuel that accelerates the fuel. The mathematics spiral rapidly into impossible territory. Consider a spacecraft with a mass of 1,000 kilograms that you want to accelerate to just 10% of light speed, a velocity of 30,000 kilometers per second. Let's assume you're using the most efficient chemical rocket fuel imaginable, releasing energy at the theoretical maximum for chemical reactions. How much fuel would you need? The answer is absurd. You would need more fuel than exists in several solar systems worth of matter. The ratio of fuel to payload would be so extreme that the numbers become meaningless. And that's just to reach 10% of light speed. To go faster, to approach even half of light speed, the fuel requirements grow exponentially. At 90% of light speed, you're in the realm of needing fuel masses equivalent to entire galaxies. Chemical rockets simply cannot do the job, not even in principle. The energy density of chemical bonds, the amount of energy you can extract from each kilogram of fuel, is far too low. You would need something far more energetic, far more efficient at converting mass to kinetic energy. You would need nuclear reactions or even matter-antimatter annihilation, the most energy-dense process physics allows. Matter-antimatter reactions are beautifully efficient. When a particle meets its antimatter counterpart, they annihilate completely, converting 100% of their mass into energy according to E equals mc squared. This is the theoretical maximum for energy extraction. You cannot be more efficient than total mass conversion, and yet even with matter-antimatter fuel the rocket equation remains formidable. To accelerate a modest spacecraft to 90% of light speed using perfect matter, antimatter annihilation would require carrying antimatter equal to several times the ship's mass. And antimatter doesn't exist naturally in meaningful quantities. We'd have to manufacture it, particle by particle, in accelerators, expending enormous amounts of energy to create each microscopic quantity. The energy cost of producing the antimatter would far exceed the energy you'd get from annihilating it. There's also the problem of storage. Antimatter cannot touch normal matter without immediately annihilating. You'd need some kind of magnetic containment system, which adds mass to your spacecraft, requiring even more fuel. And the containment system would need power, and power systems have mass, and round the spiral goes. Some have proposed alternative propulsion methods that don't rely on carrying fuel aboard the spacecraft. Nuclear pulse propulsion, for instance, imagines accelerating a vessel by detonating nuclear bombs behind it, riding the shockwave like a ship on an infinite series of explosions. Project Orion, a serious if somewhat terrifying proposal from the 1950s, calculated that such a system could theoretically reach a few percent of light speed. Other concepts involve collecting fuel from the interstellar medium as you travel. The Bussard ramjet, proposed by Robert Bussard in 1960, imagined a vast magnetic scoop hundreds of kilometres wide, gathering hydrogen atoms from space and fusing them for propulsion. The interstellar medium is sparse, only about 1 atom per cubic centimetre, but at high enough velocities, you'd sweep up sufficient material to sustain fusion. The problem is that you need to already be travelling at a significant fraction of light speed for the ramjet to work, and getting up to that initial velocity requires conventional rockets with all their fuel mass limitations. And as you approach relativistic speeds, the hydrogen atoms you're collecting would strike your magnetic scoop with tremendous energy, creating drag that works against your acceleration. The faster you go, the more the interstellar medium resists your passage. Every solution creates new problems. Every clever engineering approach runs into fundamental physical limitations. The rocket equation is not just an inconvenience to be solved with better technology. It's a mathematical expression of how difficult it is to change velocity when you must carry your energy source with you. And as the target velocity approaches light speed, the difficulty doesn't just increase, it becomes infinite. Which leads us naturally to consider whether we might sidestep the rocket equation entirely, whether there might be ways to reach distant stars without actually travelling through the space between them. If you cannot go faster than light through space, perhaps you could... Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. Perhaps you could go around the limitation by changing space itself. This is the tantalizing possibility suggested by certain solutions to Einstein's equations of general relativity. The equations that describe how mass and energy curve space-time admit some exotic possibilities, mathematical solutions that seem to allow shortcuts through the universe. The most famous of these is the wormhole, technically called an Einstein-Rosen bridge. Imagine space-time as a 2-dimensional sheet. A massive object like a star creates a depression in this sheet, a curve that we experience as gravity. Now imagine that somewhere else, perhaps light years away, there's another depression in this sheet. A wormhole would be a tunnel connecting these 2 depressions, a shortcut through the fabric of space-time itself. If such a tunnel existed, you could enter one mouth of the wormhole, travel through this higher dimensional passage, and emerge from the other mouth, having crossed vast distances without ever exceeding light speed through normal space. From the perspective of someone watching from outside, you would disappear at one location and reappear at another, having traversed light years in what might be moments of your own time. The mathematics of general relativity doesn't forbid this. In fact, the equations naturally produce wormhole solutions when you explore them thoroughly. But there's an enormous difference between a mathematical solution and a physical reality. Just because the equations allow something doesn't mean the universe actually creates it, or that we could use it even if it existed. The first problem is stability. The wormhole solutions that emerge from general relativity are typically unstable. They would collapse almost instantly, snapping shut before anything could pass through. To keep a wormhole open, you would need to thread it with what physicists call exotic matter, a form of matter with negative energy density. This is not antimatter, which has positive energy. This is something far stranger, matter that pushes space apart rather than pulling it together. We have theoretical reasons to think exotic matter might exist under certain quantum conditions. The Casimir effect, where 2 metal plates in a vacuum experience an attractive force, is sometimes cited as evidence of negative energy densities in quantum fields. But creating enough exotic matter to stabilize a wormhole, to hold open a tunnel through space-time large enough for a spacecraft to traverse, is so far beyond our capabilities that it ventures into pure speculation. There's also the causality problem we encountered earlier. If you could travel through a wormhole, and if you could move one mouth of the wormhole relative to the other at high velocity, you could create a time machine. The time dilation between the two mouths would mean that entering one mouth could bring you out the other in the past. And as we've discussed, allowing time travel creates causality violations. Paradoxes that suggest the universe doesn't permit such configurations to exist. Some physicists argue that quantum effects would prevent a wormhole from becoming a time machine, that radiation would build up and destroy the wormhole the instant it threatened to violate causality. Others suggest that wormholes might exist but only allow one-way travel, preventing closed causal loops. Still others propose that the universe simply doesn't allow wormholes to form in the first place. That there's some principle we haven't yet discovered that forbids them. Another exotic space-time manipulation is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This theoretical concept imagines contracting space-time in front of a spacecraft while expanding it behind, creating a wave of distorted space that carries the ship along. The ship itself would never exceed light speed relative to the local space-time around it, but space itself would be moving, carrying the vessel faster than light relative to distant observers. The mathematics work, in a purely theoretical sense. But the energy requirements are staggering. Early calculations suggested you would need the mass energy of an entire planet, converted entirely into exotic matter with negative energy density. Later refinements reduced this to merely the mass energy of Jupiter, still obviously impossible with any conceivable technology. And there's a deeper problem. To create the warped space-time bubble, you would need to already be at your destination to set it up. You cannot manipulate space-time from within the bubble you're trying to create. It's a bit like trying to lift yourself by your own bootstraps. The physics may allow the configuration to exist once established, but establishing it in the first place seems to violate other fundamental principles. These exotic solutions to the lightspeed problem share a common feature. They're all theoretically possible in the sense that they don't obviously violate known physical laws, but they require conditions or materials so far removed from anything we can actually produce that they remain firmly in the realm of speculation. They're intellectual exercises, explorations of what the equations permit, rather than practical engineering proposals. The universe, it seems, allows us to imagine faster-than-light travel in certain contrived scenarios, while simultaneously making those scenarios practically unreachable. It's as if reality is taunting us, showing us mathematical doorways to impossible journeys, while ensuring the doors remain firmly locked. But there's another layer to consider beyond these exotic solutions, one that reveals why the energy requirements for any form of faster-than-light travel grow without bound. Let's return to the fundamental energy problem and explore just how extreme it becomes as you approach light speed. We've discussed that accelerating mass to light speed requires infinite energy, but let's put some actual numbers to the challenge to understand just how impossible this is, even at velocities well below the cosmic limit. Consider a spacecraft with a mass of just 10,000 kilograms, about the size of a large satellite. Now let's imagine accelerating this modest vessel to 99% of the speed of light. How much energy would this require? The kinetic energy of an object in Newtonian physics is 1/2 mass times velocity squared. But this formula breaks down at relativistic speeds. The correct formula involves that gamma factor we discussed earlier, and it produces results that quickly become astronomical. At 99% of light speed, accelerating our 10,000 kilogram spacecraft would require about 6.3 times 10 to the 21st joules of energy. That number is difficult to comprehend, so let's find some comparisons. The total energy consumption of human civilization for an entire year is roughly 6 times 10 to the 20 joules. So accelerating a single small spacecraft to 99% of light speed would require more energy than all of humanity uses in a year, for all purposes, across the entire planet. And that's just to reach 99%, not light speed itself. At 99.9% of light speed, the energy requirement increases by more than a factor of 3. At 99.99%, it more than doubles again. The pattern continues, the energy growing without limit as you approach the cosmic boundary. To actually reach light speed would require literally infinite energy, more than exists in the entire observable universe. Where would such energy come from? The most energetic processes we know of are nuclear reactions. The Sun produces about 3.8 times 10 to the 26 joules per second through nuclear fusion. To power a hypothetical spacecraft to 99% of a light speed, the Sun would need to devote its entire output, all the energy it radiates in all directions into space for about 16 seconds, just to accelerate one 10,000 kilogram spacecraft. And this is only the kinetic energy, the energy needed to change the spacecraft's velocity. It doesn't include the energy needed to produce the antimatter fuel, to maintain life support systems, to operate the ship's equipment, to slow down at the destination. When you account for all these factors, the energy budget becomes even more impossible. Some have proposed harvesting energy from astronomical sources, a Dyson sphere, a hypothetical megastructure that surrounds a star and captures all its radiant energy, could provide power on the scale needed for relativistic travel. But building such a structure would require disassembling entire planets, would take centuries or millennia even with advanced automation, and would solve only the energy generation problem, not the fundamental issue of how to convert that energy into propulsion efficiently. There's also the problem of what happens to all that energy when you want to slow down. At 99% of light speed, your spacecraft has enormous kinetic energy. To stop at your destination requires dissipating all that energy. You need equally powerful braking systems, equally vast fuel reserves for deceleration. A spacecraft is not just an engine. It's two engines, one to speed up and one to slow down, each requiring fuel that must be carried from the beginning of the journey. The energy requirements reveal something profound about the structure of the universe. The speed of light is not just fast, it's a boundary that's protected by exponentially increasing energy demands. Nature doesn't just say you cannot exceed light speed. It makes the attempt require more and more resources the closer you get, until at the limit itself the requirement becomes infinite. It's a soft wall that becomes increasingly hard, approaching absolute impenetrability as you approach the ultimate speed. Even if we imagine civilizations far more advanced than our own, even if we grant them near magical technologies and access to the energy output of entire galaxies, they would still face these same fundamental limitations. The laws of physics don't change based on technological sophistication. A sufficiently advanced civilization might be able to accelerate small probes to a significant fraction of light speed, perhaps even to 99.9% or beyond. But reaching actual light speed would remain forever out of reach. This brings us to a question worth considering. If we accept that light speed is impossible, what velocities are actually achievable, and what would interstellar travel look like within the constraints physics imposes? Let's ground ourselves in what might actually be possible, what velocities we could realistically achieve with technologies that don't require exotic matter or infinite energy. This is the domain of interstellar travel proposals that serious scientists and engineers have actually developed. Concepts that respect known physics while pushing the boundaries of what's conceivable. The fastest spacecraft humanity has ever built, Voyager 1, is currently travelling at about 17 kilometers per second relative to the Sun. That's fast by everyday standards, but it's only about 0.006% of the speed of light. At that velocity, it would take more than 70,000 years to reach the nearest star system, Alpha Centauri, just over 4 light-years away. Chemical rockets have taken us to the Moon and sent probes to the outer planets, but they're fundamentally limited by the energy density of chemical bonds. To go significantly faster, we need more energetic propulsion systems. Nuclear propulsion offers one possibility. The Project Orion concept we mentioned earlier, propelling a spacecraft with nuclear explosions, could theoretically reach velocities of a few percent of light speed. Imagine a spacecraft with a massive pusher plate on one side. You would eject nuclear bombs behind this plate, detonating them at carefully timed intervals. Each explosion would vaporize a small amount of the plate material, which would strike the plate and transfer momentum to the spacecraft. It's violent, terrifying, and theoretically possible. The Nuclear Test Ban Treaty made atmospheric testing of such a system politically impossible, but the physics work. At a few percent of light speed, say 3%, the journey to Alpha Centauri would take about 140 years. That's still multiple human lifetimes, but it's at least conceivable. A generation ship carrying a crew who would live their entire lives in transit could potentially make such a journey. Their children or grandchildren would arrive at a new star system, would see worlds no human had ever witnessed. Another possibility is nuclear fusion propulsion, harnessing the same process that powers stars. Fusion releases far more energy per unit mass than chemical reactions, though much less than matter-antimatter annihilation. A fusion rocket could potentially accelerate a spacecraft to perhaps 10% of light speed, reducing the journey to Alpha Centauri to about 40 years. 10% of light speed is fast enough to make interstellar travel barely feasible within a human lifetime, at least if you're willing to spend your entire adult life in transit. At this velocity, time dilation becomes noticeable. The travellers would age slightly less than people remaining on Earth, though the effect would be small, only about 0.5%. Still, it's the first glimmer of relativistic effects, a hint of the strange physics that dominates at higher velocities. For higher speeds, we need even more exotic but still physically plausible systems. Light sails offer an interesting possibility. Imagine a vast, thin mirror, perhaps kilometres across, attached to a small spacecraft. You shine powerful lasers at this sail from Earth, or from satellites orbiting the Sun. The photons carry momentum, and when they reflect off the mirror, they transfer that momentum to the spacecraft. The advantage of a light sail is that you don't have to carry fuel. The energy source remains behind, beaming power to the departing ship. The Breakthrough Starshot Initiative has proposed using this concept to send small probes to Alpha Centauri at 20% of light speed. These would be tiny spacecraft, mere grams in mass, each with a sail a few meters across. An array of powerful ground-based lasers would accelerate them during the initial phase of their journey. At 20% of light speed, the journey to Alpha Centauri would take about 20 years. Time dilation would be noticeable, with the probes aging about 2% slower than Earth-based clocks. They couldn't slow down or stop, would flash past the Alpha Centauri system at tremendous velocity, gathering data for a few hours at most before disappearing into the cosmic void. But they could send back images and measurements, could tell us what lies in another star system. These velocities, from a few percent to perhaps 20% of light speed, represent the realistic outer limits of what we might achieve with known physics and conceivable engineering. They're fast enough to make interstellar travel possible in principle, slow enough that we don't run into the insurmountable relativistic barriers that make light speed impossible. But even at these velocities, the challenges are immense. Interstellar space is not empty. It contains dust, gas, the occasional stray atom. At 20% of light speed, colliding with even a tiny dust grain releases tremendous energy. A speck of matter a millimetre across would strike with the force of a hand grenade. Any spacecraft travelling at such velocities would need substantial shielding, adding mass and complexity. And there's the problem of navigation and communication. At these distances and velocities, Earth would be years away by radio signal. Commands sent from home would arrive long after they were relevant. The spacecraft would need to be autonomous, capable of making decisions without guidance, of responding to unexpected situations without consulting mission control. We would be sending not just machines into the void, but intelligent agents, representatives of humanity who would never return, would perhaps never even communicate successfully with their builders. So we arrive at a realistic picture of humanity's possible future among the stars, one bounded by physics, by energy limitations, by the fundamental structure of space-time. We will not zip between stars in days or weeks. We will crawl across the cosmic distances at velocities that seem fast by human standards but glacial compared to the cosmic speed limit. And perhaps this is how it should be. How the universe is meant to be experienced. Let's consider what this means for the vast cosmic distances and the isolation it imposes. The light speed limit doesn't just constrain how fast we can travel. It fundamentally shapes the structure of the cosmos we inhabit, determines what is and isn't accessible, creates a universe of isolated islands separated by oceans of space. Understanding this isolation helps us appreciate why the cosmic speed limit exists and what it means for any civilization that arises in this universe. Let's begin with scale. The distance to the nearest star, Proxima Centauri, is about 4.2 light-years. This means that light, travelling at the cosmic speed limit, takes 4.2 years to make the journey. Nothing can make the journey faster, and most realistic technologies would take far longer. At 10% of light speed, a respectable velocity for a fusion-powered spacecraft, the journey would take 42 years. But Proxima Centauri is our closest neighbour. Unusually near in cosmic terms, most stars are far more distant. The Milky Way galaxy is about 100,000 light-years across. To cross from one side to the other at light speed would take 100,000 years. At 10% of light speed, 1,000,000 years. The distance to the Andromeda Galaxy, our nearest galactic neighbour, is about 2.5 million light-years. These distances are not merely large, they are structured by the speed of light itself. When we measure cosmic distances in light-years, we're using the cosmic speed limit as our ruler. We're saying that this much space is equivalent to this much time for light, and since nothing can exceed light speed, these distances translate directly into minimum travel times. The universe is not just big. It's measured in units of time at maximum possible velocity. This has profound implications for any form of interstellar civilization. Even with perfect technology, even with spacecraft that could somehow reach 99.99% of light speed, the galaxy would still be vast beyond imagination. Travel between distant stars would still take decades, centuries, millennia. Real-time communication would be impossible. Cultural exchange would happen across generations. Not in conversation. Imagine trying to maintain a coherent civilization spread across light-years. A colony 10 light-years from Earth would receive news from home 20 years after events occurred. Their responses would take another 20 years to return. Any conversation would span 40 years for a single exchange. No one could maintain a dialogue across such distances. Political unity would be impossible. Cultural divergence would be inevitable. The light speed limit enforces a kind of cosmic provincialism. Each star system becomes its own isolated realm, able to send messages to neighbouring systems, but unable to maintain the kind of tight integration that we associate with unified civilizations. The ancient empires of Earth, Rome or China or the Mongols, succeeded through rapid communication and movement. Messengers could cross their territories in weeks or months. Orders could be issued and obeyed. Rebellions could be suppressed. But an interstellar empire is a contradiction. You cannot govern what you cannot reach in a reasonable time. You cannot enforce laws when commands take years or decades to arrive. You cannot suppress independence when rebels have years to prepare before your response reaches them. The light speed limit doesn't just slow travel. It fragments any attempt at large-scale organisation across the stars. Some science fiction has imagined ways around this, answerable devices that allow faster-than-light communication, or wormholes that connect distant regions of space. But these are fantasy, violations of known physics. The reality is more isolating. Each star system is fundamentally alone, separated from its neighbours by distances that cannot be quickly crossed, that impose years or decades or centuries between contact. and this isolation might be intentional in a sense. Not that the universe was designed with consciousness in mind, but that the structure of physics naturally creates conditions where complexity can develop without immediate interference. If faster-than-light travel were possible, if any civilization could reach any other civilization quickly, the galaxy might be a far more violent and chaotic place. Isolation provides protection, ensures that emerging civilizations have time to develop, to mature, without immediate threat from aggressive neighbours. The cosmic speed limit creates a universe of light cones, regions of space-time that can be causally connected to a given event. Your light cone is all the space you could possibly reach, all the events you could possibly influence, given the speed of light and the age of the universe. Everything outside your light cone is inaccessible, unreachable, separated from you by more distance than light has had time to cross. For humanity on Earth, our light cone extends about 13.8 billion light-years in every direction, to the edge of the observable universe. But most of that space is forever unreachable, racing away from us faster than we could ever follow due to the expansion of space itself. Our practical light cone, the region we could conceivably reach or influence, is far smaller, perhaps a few million light-years at most, and realistically much less. Within this limited region, there may be other civilizations. The galaxy contains hundreds of billions of stars, many with planets, some potentially harbouring life. Statistical arguments suggest we might not be alone, but the distances between civilizations would be vast. Even if there are 1 million technological civilizations in our galaxy, each would be separated from its neighbours by thousands of light-years on average. They would be like ships passing in the night, able to perhaps detect each other's presence, but unable to visit, unable to communicate in any meaningful real-time sense. The light speed limit thus answers one of the great paradoxes of astronomy. If the universe is so vast and so old, if there are billions of stars and potentially millions of civilizations, where is everybody? Why haven't we been visited? Why is the sky not filled with radio chatter from alien civilizations? The answer might be simply that the distances are too great, the speed limit too absolute, the isolation too complete. And so we come to understand that the universe's structure, shaped by the cosmic speed limit, creates a particular kind of reality, one where complexity and life can emerge in protected pockets, where civilizations can develop without interference, but where contact between those civilizations requires patience measured in generations, requires accepting isolation as the default state. Let that thought settle as we move forward into questions of what this means for time itself, and how the nature of light speed shapes not just distance but duration. We've been discussing space and time as if they were separate things, two different dimensions of reality. But one of Einstein's deepest insights, perhaps the most revolutionary aspect of relativity, is that space and time are not separate at all. They're woven together into a single four-dimensional fabric called spacetime. Understanding this unity helps explain why the speed of light is what it is, and why it must be a universal constant. In our everyday experience, space and time seem completely different. Space is the dimensions we move through, forward and back, left and right, up and down. Time is the dimension we're dragged through helplessly, always moving from past to future at 1 second per second. We can turn around in space, can face any direction we choose, but we cannot turn around in time, cannot reverse our temporal motion or even pause it. But this distinction between space and time, so obvious in daily life, breaks down when we examine motion at high velocities. What one observer measures as purely spatial distance, another observer moving relative to the first might measure as a mixture of space and time. What seems like pure time passage to one observer appears as both time and space to another. The distinction is not fundamental, but depends on your reference frame, on how you're moving. Imagine two events in space-time, a firecracker exploding at noon, and that same firecracker's flash reaching your eye a fraction of a second later. For you standing still, these are two events separated in time, the explosion and your perception of it. But for someone flying past in a spacecraft at high velocity, these two events are separated differently. They measure a different time interval between them and a different spatial distance. Both measurements are equally valid, equally real. What remains constant, what all observers agree on regardless of their motion, is something called the space-time interval. This is a mathematical combination of the spatial distance and the time interval between events, calculated in a specific way that Einstein's equations dictate. The space-time interval is the same for all observers, even though they disagree about how much of that interval is space and how much is time. This invariant interval is the true geometry of the universe. Space and time are like the two dimensions of a sheet of paper. You can rotate the paper, can change which direction you call horizontal and which you call vertical. But the distance between 2 points on the paper, measured along the paper's surface, doesn't change no matter how you rotate it. Similarly, the space-time interval between two events doesn't change no matter how you're moving, even though your measurements of space and time individually do change. The speed of light emerges naturally from this geometry. It's the conversion factor between space and time, the ratio that tells you how much space is equivalent to how much time in the calculation of the space-time interval. In units where we measure time in years and distance in light years, the speed of light is simply 1 light year per year. It's the speed at which the spatial distance travelled exactly equals the time elapsed, where space and time contribute equally to the space-time interval. This is why light travels at the speed it does. It's not that light _4_ to go at 300,000 kilometers per second. Rather, light follows the null geodesics of space-time, the path through four-dimensional space-time geometry, where the space-time interval is 0. These are the paths where the time component and the space component exactly cancel out, where something can traverse space without experiencing time. For massive objects, for anything that experiences the passage of time, such paths are forbidden. You cannot travel along a path where the space-time interval is 0 because doing so would mean experiencing no time, existing without duration. You would be frozen, timeless, like a photon. The paths available to massive objects are those where time predominates over space, where the time-like component of motion is larger than the space-like component. This is another way of understanding why you cannot reach light speed. To do so would require transitioning from a time-like path through space-time to a null path, from experiencing time to being timeless. It would be like trying to rotate a line in three-dimensional space until it became a point. The geometry doesn't allow it. The mathematics forbid the transformation. There's a beautiful symmetry here. Light exists at the boundary between space and time, the place where they're perfectly balanced. Slower than light, and you're moving primarily through time, experiencing duration as you traverse space. At light speed, space and time contributions are equal. Faster than light would mean moving primarily through space with time as the smaller component, which would require time moving backward from your perspective, causality violation, paradox. The unity of space-time thus enforces the cosmic speed limit. It's not an arbitrary rule imposed on the universe. It's a consequence of the geometric structure of reality itself. Space and time are two aspects of a single thing, and the speed of light is the fundamental rate of exchange between them, the cosmic conversion factor. Understanding this helps us see why every attempt to exceed light speed fails. You're not fighting against a speed limit. You're fighting against the structure of existence itself. Which brings us to something equally important: how moving through this unified space-time fabric affects the aging process and the fundamental flow of time. There's a famous thought experiment in Relativity that seems to create a paradox but actually reveals deep truths about time. It's called the twin paradox, and it goes like this. Imagine two twins, one who stays on Earth and one who travels into space at high velocity, then returns. When the travelling twin comes back, they've aged less than the twin who stayed home. Time has literally passed more slowly for them. But here's the apparent paradox. According to relativity, all motion is relative. From the travelling twins' perspective, they were sitting still in their spacecraft while Earth moved away and then returned. Shouldn't the earthbound twin be the one who aged less? How can relativity say both twins aged less than the other? That would be a logical contradiction. The resolution of this paradox teaches us something crucial about the nature of time and motion. The situation is not actually symmetric. The travelling twin must accelerate, must change velocity to turn around and come home. The earthbound twin experiences no such acceleration. They remain in an inertial reference frame, moving at constant velocity while the travelling twin does not. This asymmetry is real and physical. The travelling twin feels forces during acceleration. They're pressed into their seat. They know they're the one who's changing velocity. And it's this acceleration, this change in velocity that breaks the symmetry and makes the twins' experiences genuinely different. When you accelerate in relativity, you're changing your path through space-time, tilting your trajectory through the four-dimensional geometry. This tilting is what causes the differential aging. Let's make this concrete with numbers. Suppose the travelling twin goes on a journey to a star 10 light-years away, travelling at 90% of light speed. The earthbound twin measures the journey as taking just over 11 years each way, about 22 years total. But for the travelling twin, time dilation means their clock runs slower. At 90% of light speed, time dilation factor is about 2.3. So the travelling twin experiences the journey as taking only about 9.6 years, not 22 years. When they return, the earthbound twin has aged 22 years. The travelling twin has aged less than 10 years. Both are correct in their own frame of reference. The travelling twin really did experience less time. Their heart beat fewer times. They had fewer thoughts. Fewer of their cells divided. They are biologically younger. This isn't science fiction. It's measured reality. We've confirmed time dilation in countless experiments. Atomic clocks flown in airplanes run slightly slower than identical clocks left on the ground. Particles accelerated to near light speed, and accelerators live longer than their stationary counterparts, decaying more slowly because less time passes for them. Even GPS satellites must account for time dilation, both from their velocity and from the slightly different gravitational field they experience in orbit. The twin paradox reveals that time is not universal, not absolute, not the same for everyone. It's personal, dependent on your path through space-time. Two people who begin at the same event and end at the same event can experience vastly different durations between those events if they take different paths through space-time. Think of it like two travellers going from one city to another by different routes. One takes a straight highway, the other takes a winding scenic route. They both start at the same place and end at the same place, but they travel different distances. In space-time, different paths between the same two events can have different durations. The distance through time is not fixed but depends on the route you take. There's something profound and almost melancholic about this. It means that as we move through space, as we accelerate and change direction, we're choosing how much time we experience. A person who spends their life travelling at high velocity will age less than someone who stays relatively stationary. They'll experience less of existence, will have fewer heartbeats, fewer moments of consciousness. But from their perspective, nothing seems different. Time always flows at 1 second per second for you, no matter how fast you're moving. It's only when you compare with someone who took a different path that the difference becomes apparent. The traveller doesn't feel time passing slowly. They simply arrive at the reunion younger than their twin, surprised to find how much time has passed for others. This property of time, its flexibility, its dependence on motion, is another reason why light speed is special. At light speed, time dilation becomes infinite. An infinite amount of external time passes in zero experienced time. The path through space-time becomes null. timeless, existing without duration. This is the limiting case, the boundary where the concept of time flow breaks down completely. For beings like us who exist in time, who experience duration and change and aging, light speed represents a boundary we can approach but never reach. We can slow our clocks relative to the external universe, can travel into the future by moving fast and returning to find centuries have passed, while we aged only years. But we cannot stop time entirely. We cannot become timeless while remaining conscious, existing beings. The twin paradox, then, is not really a paradox, but a revelation about the nature of temporal existence. Time is woven into motion through space. How you move determines how much time you experience. And the faster you move, approaching the cosmic speed limit, the less time flows for you relative to the universe around you. Let's step back now and look at how this understanding of space-time relates to the quantum world, where strange things happen that seem to challenge our neat relativistic picture. We've been exploring relativity, the physics of the very fast and the very large. But there's another fundamental theory of modern physics, quantum mechanics, the physics of the very small. At first glance, these two theories seem to describe different realms. Relativity governs planets and stars and spacecraft. Quantum mechanics governs atoms and particles. But they intersect in interesting ways, and when we look carefully, we find that quantum mechanics also respects the cosmic speed limit, though in ways that can seem strange. Quantum mechanics is famous for its weirdness. Particles can be in multiple states simultaneously, can tunnel through barriers they shouldn't be able to cross, can be entangled with each other across arbitrary distances. This last property, quantum entanglement, sometimes seems to suggest faster-than-light communication. But when we examine it carefully, we find that it doesn't actually violate the cosmic speed limit. Imagine two particles created together in such a way that their quantum states are correlated. We call this an entangled state. You can separate these particles by vast distances, light years if you want. And here's the strange part. When you measure some property of one particle, say its spin, the other particle's spin instantly becomes determined, even though it's light years away. The correlation is instantaneous. This seems to violate relativity. How can information about the measurement of one particle reach the other particle faster than light? Einstein called this spooky action at a distance and was deeply troubled by it. He thought it suggested quantum mechanics was incomplete, that there must be hidden variables determining the particle's states in advance. But we've since confirmed through experiment that quantum mechanics is correct and that entanglement is real. The particles truly are in indefinite states until measured, and the measurement results truly are correlated instantaneously across arbitrary distances. This has been verified countless times with increasing precision. It's not a measurement problem or a misunderstanding, it's how reality actually works. So does this mean information travels faster than light? No, and here's why. While the correlation is instantaneous, you cannot use entanglement to send information. Suppose you measure your particle and find it as spin up. You now know the distant particle will be measured as spin down. But the distant observer, before they make their measurement, has no way to know that you've measured your particle. The results they observe appear random to them. Only when you compare notes later, communicating through normal light speed limited channels, do you discover the correlation. Entanglement creates correlations without communication. The particles' states are linked, but no information flows between them faster than light. It's as if the universe maintains a consistency in its quantum states, ensures that correlated measurements give correlated results, without any signal travelling between the particles. This is deeply strange, philosophically puzzling, but it doesn't violate causality or allow faster-than-light communication. There's another quantum phenomenon worth considering: quantum tunneling. Particles can sometimes appear on the other side of energy barriers they shouldn't classically be able to cross. A particle tunneling through a barrier seems to traverse the barrier without spending time in the middle, which might suggest faster than light motion through the barrier. But when we analyse this carefully, we find that quantum tunnelling also respects the speed of light limit. The particle doesn't actually travel faster than light through the barrier. Instead, quantum mechanics allows the particle a small probability of being found on the other side, determined by the barrier's properties and the particle's wave function. The process doesn't involve classical motion at all, and no information or causation propagates faster than light. What about virtual particles, the quantum fluctuations that fill the vacuum of space? These can briefly pop into existence, seemingly violating energy conservation for tiny fractions of time allowed by Heisenberg's uncertainty principle. Do these virtual particles move faster than light? Again, the answer is no. Virtual particles are mathematical constructs in quantum field theory, tools we use to calculate probabilities of real particle interactions. They're not real in the sense that you can detect them or use them to send information, and the interactions they represent when we calculate them properly always respect the light speed limit for any physical effect that propagates from one place to another. The unification of quantum mechanics and relativity is an active area of research. Quantum field theory combines the two frameworks, describing particles as excitations of quantum fields that permeate spacetime. In this formulation, the speed of light emerges naturally as the maximum speed at which field excitations can propagate, the maximum speed at which quantum information can spread. One of the requirements for any quantum field theory to be consistent is called causality. Effects cannot precede their causes. Measurements at one location cannot instantaneously affect measurements at distant locations in ways that could be detected. When physicists construct quantum field theories, they must ensure these causality conditions are satisfied, and it turns out that requiring causality automatically imposes the light speed limit. You cannot have faster than light propagation without violating causality, and you cannot violate causality without making the theory mathematically inconsistent. So quantum mechanics, despite its weirdness, despite entanglement and tunnelling and virtual particles, fully respects the cosmic speed limit. The speed of light governs not just classical motion but quantum processes as well. It's built into the deepest level of physical law we know. Whether we're talking about planets or particles, about gravity or quantum fields, the same limit applies. Nothing physical can exceed light speed. This consistency across all domains of physics suggests that the light speed limit is truly fundamental, not an accident of one particular theory, but a basic feature of how reality is structured. And understanding this helps us appreciate why all attempts to circumvent the limit fail. We're not fighting against one law of physics. We're fighting against the entire consistent structure of physical reality. From here, let's turn our attention to what happens at the limit itself, to photons experiencing zero time and what this tells us about the nature of existence. We've discussed how impossible it is for anything with mass to reach light speed. But photons do travel at light speed. They must. They cannot slow down or speed up. What is existence like from a photon's perspective? What does the universe look like when you're travelling at the cosmic speed limit? The answer is both simple and strange. A photon doesn't experience anything. From its perspective, if we could adopt such a perspective, zero time passes between its creation and its destruction. The entire journey, whether it lasts a nanosecond or a billion years from our viewpoint, happens in a single instant from the photon's reference frame. Consider a photon emitted from a star in the Andromeda Galaxy, 2.5 million light-years away. From Earth, we watch this photon's journey span millions of years, crossing the vast gulf between galaxies, maintaining its direction and energy across incomprehensible distances. We eventually detect it when it strikes a detector or enters someone's eye. 2.5 million years have passed from our perspective between emission and detection, but for the photon itself, the journey is instantaneous. It's emitted and absorbed in the same moment. No duration intervenes. The photon doesn't experience the passage of time. Time dilation at light speed is infinite, so infinite time in our frame corresponds to zero time in the photon's frame. Moreover, from the photon's perspective, space itself contracts to zero in the direction of travel. Length contraction at light speed is also infinite. The photon experiences zero distance between emission and absorption. The star where it was created and the detector where it's absorbed are at the same location from its viewpoint. All of space along its trajectory collapses to a single point. This is difficult to wrap our minds around because we exist in time, we experience duration, we traverse space. But for light, these concepts don't apply. Light exists at the boundary where space and time cease to have their usual meaning. It connects distant events without experiencing the separation between them. This timeless, spaceless existence of photons reveals something profound about what light speed represents. It's not just fast. It's the speed at which the universe as we know it dissolves. At light speed, the familiar dimensions of existence, time and space shrink to nothing. Cause and effect become simultaneous. Beginning and ending merge into a single eternal now. For conscious beings, for anything that exists in time and experiences the flow of moments, this state is unreachable. Consciousness requires time. Thought is a process, something that unfolds, that has a before and an after. Without time, there can be no experience, no awareness, no existence in any meaningful sense. This is perhaps the deepest reason why we cannot reach light speed. It's not just that we lack the energy, or that the physics prevents it. It's that light speed is a state of being fundamentally incompatible with existence as we know it. To travel at light speed would be to cease experiencing, to become timeless, to leave the realm of consciousness and thought and being. Photons can exist at light speed because they don't experience anything. They're not conscious. They don't think or feel or perceive. They simply connect points in space-time, carry energy from one place to another without experiencing the journey. They're more like geometric features of space-time than objects travelling through it. There's something both beautiful and melancholy about this. Light connects the universe, carries information about distant stars to our eyes, makes vision and life and knowledge possible. The sun's light reaches Earth, and this energy flow enables the entire web of life on our planet. Light from ancient galaxies reaches our telescopes, telling us about the universe billions of years in the past. Everything we see because of light, but the light itself experiences none of this. The photons that allow us to perceive the universe don't perceive anything themselves. They're messengers without consciousness, connectors without experience. They travel from star to eye, from galaxy to detector, linking everything while experiencing nothing. This suggests that the cosmic speed limit is not just about velocity, but about the boundary between existence and non-existence in time. Below light speed you exist in time, experience duration, can think and feel and be aware. At light speed you escape time, but in escaping it, you cease to exist as an experiential being. You become a mathematical abstraction, a geometric feature, a path through space-time rather than a traveller along that path. For humanity, for any life or consciousness in the universe, this boundary is absolute. We can approach it, can harness it, can use light to see and communicate and understand, but we cannot cross it while remaining ourselves. The cosmic speed limit is the boundary of experiential existence, the edge beyond which consciousness cannot go, and perhaps this is as it should be. Perhaps there's a fundamental divide in the universe between things that exist in time, that experience and change and evolve, and things that exist outside of time, that connect moments without experiencing them. Light occupies this second category, serving as the bridge between all the conscious beings in the first category, which leads us to contemplate what all of this means for the larger structures in the universe and how the cosmic speed limit shapes even the expansion of space itself. The cosmic speed limit doesn't just affect how fast we can travel. It determines what we can ever reach, what we can ever know, what parts of the universe are accessible to us even in principle. Combined with the expansion of space itself, the light speed limit creates boundaries beyond which the universe becomes forever unreachable. Regions that are receding from us faster than we could ever pursue them. Our universe is expanding. Every distant galaxy is moving away from every other distant galaxy, not because they're travelling through space, but because space itself is expanding, carrying the galaxies with it. This expansion was discovered by Edwin Hubble in the 1920s and has been confirmed and measured with increasing precision ever since. The expansion means that distant galaxies are moving away from us at velocities proportional to their distance. The farther away a galaxy is, the faster it recedes. This is described by Hubble's law. Recession velocity equals the Hubble constant times distance. And here's the crucial point. There exists a distance beyond which galaxies are receding from us faster than the speed of light. Wait, you might think. Didn't we just spend many chapters proving that nothing can exceed light speed? How can galaxies recede faster than light? The answer is subtle. The galaxies themselves aren't moving through space faster than light. Instead, the space between us and them is expanding. They're being carried by the expansion of space, and there's no limit to how fast space itself can expand. This creates what we call the cosmological horizon, a boundary beyond which we can never reach, can never communicate with, can never observe directly. Galaxies beyond this horizon are receding so fast that light leaving us now will never reach them. The expanding space between us and them stretches the light, slows its progress, keeps it from ever completing the journey. Currently, this horizon is about 16 billion light-years away. Any galaxy more distant than this is receding faster than light and is forever beyond our reach. We can see some of these galaxies because the light we're observing now left them billions of years ago when they were closer, when the expansion hadn't yet carried them beyond the horizon. But we're seeing them as they were in the ancient past. We can never see them as they are now, can never communicate with them, can never send a spacecraft to visit them. This is a profound form of cosmic isolation. The universe contains perhaps 2 trillion galaxies in the observable universe, but most of them are beyond our cosmic horizon. We can see their ancient light, can study what they were like billions of years ago, but we can never interact with them, never know their current state, never influence or be influenced by them. Perhaps this isolation serves a purpose in the evolution of complexity. If every region of space could instantly affect every other region, if there were no light speed limit and no cosmic horizons, the universe might be too connected, too chaotic, too uniform. The isolation created by light speed and cosmic expansion allows different regions to evolve independently, to develop their own character, to create diverse structures and patterns. We find ourselves in a universe with boundaries, with limits, with regions forever beyond reach. This might seem frustrating, a cosmic cruelty that places wonders just beyond our grasp. But it's also what makes our particular region of space special, unique, ours. We're not just in the universe. We're in our particular cosmic neighbourhood, with our local set of galaxies and stars and planets, separated from other neighbourhoods by unbridgeable distances. The cosmic speed limit is thus not just a rule about velocity. It's a fundamental aspect of how the universe is structured, creating boundaries and horizons, isolation and locality. It ensures that existence is diverse, that different regions can evolve independently, that the universe is not a homogeneous whole, but a collection of causally disconnected domains. And perhaps in accepting these limits, in understanding that most of the universe is forever beyond our reach, we can better appreciate what is within reach, what we can know and explore and understand. The cosmic speed limit may deny us the entire universe, but it gives us our corner of it, our home, our neighbourhood among the stars. Let that image rest with you as we continue into deeper questions about what all these physical limitations mean for meaning itself. Now that we understand the cosmic speed limit and the vast isolation it creates, we can return to a question that has puzzled astronomers and philosophers for decades. If the universe is so vast, if it contains billions of stars in our galaxy alone, and trillions of galaxies beyond, if even a tiny fraction of stars have planets suitable for life, then where are all the alien civilizations? Why haven't they visited us? Why is the sky silent? This question, first posed by physicist Enrico Fermi in casual conversation in 1950, has come to be known as the Fermi paradox. The galaxy is billions of years old. Even if civilizations are rare, even if only 1 in a million stars develops intelligent life, the sheer number of stars means there should be thousands or millions of civilizations in our galaxy alone. And if even a handful of these civilizations developed space travel, had even 1,000,000 years head start on us, they should have had time to colonize the entire galaxy many times over. Perhaps most civilizations, if they exist, choose not to expand aggressively across the galaxy. Perhaps they develop slowly, carefully, establishing colonies only nearby, maintaining connections across light years through radio and laser communications, accepting the years or decades of delay that light speed imposes. Perhaps they form small, sustainable networks of a few dozen or 100 star systems, rather than trying to colonize thousands or millions. From our perspective on Earth, such civilization 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. From our perspective on Earth, such civilizations would be nearly invisible. Their radio signals would be faint, spread across the sky, easily lost in cosmic background noise unless we knew exactly where and when to look. Their presence in nearby star systems wouldn't be obvious unless we sent probes to investigate. They might be there, a few light years away, quietly existing, and we wouldn't necessarily know. The cosmic speed limit also affects how we search for alien civilizations. We're looking for radio signals, for techno-signatures, for evidence of large-scale engineering. But we're looking at light that left those stars years or decades or centuries ago, depending on distance. If a civilization arose around a nearby star 1,000 years ago, we might not detect their presence until their signals reach us, which could take decades to centuries depending on when they started broadcasting. Moreover, civilizations might not broadcast continuously. Radio communication requires energy, and sending signals powerful enough to be detected across light years requires significant energy. A civilization might communicate for a few centuries, develop more efficient local communications, and stop broadcasting to the cosmos. We might be listening during a time when they're silent, might have missed their signals by mere centuries, a blink in cosmic time. The Fermi paradox might thus be resolved not by the absence of civilizations, but by the difficulty of detecting and reaching them across the vast distances the cosmic speed limit makes nearly unbridgeable. Civilizations might exist in reasonable numbers, scattered across the galaxy, each developing around their own star, each facing the same fundamental limitations we face. They simply cannot easily find each other or communicate with each other across the light years that separate them. This is a lonelier answer than imagining a galaxy teeming with interstellar empires and busy trade routes, but it's also perhaps a more realistic one given what we understand about physics. The universe doesn't make it easy for civilizations to find each other. The cosmic speed limit ensures that each civilization must develop in isolation, must solve its own problems, must chart its own course among the stars. And perhaps this isolation is not entirely a bad thing. It means each civilization has time and space to grow, to mature, to develop its own unique character without interference. It means the galaxy is not homogenized by a single dominant civilization, but remains diverse, containing many independent developments of life and intelligence. It means our journey into space, when we make it, will be our own, shaped by our choices and values rather than dictated by civilizations that came before. Let's continue by considering what this means practically for humanity's own future ventures into the cosmos. We've spent much of this journey exploring what we cannot do, examining the barriers physics places on our ambitions. The speed of light stands as an impassable boundary, a limit we can approach but never reach, a rule we cannot break no matter how advanced our technology becomes. There's a philosophy in this, a way of thinking about limitations that extends beyond physics into how we live and what we value. Modern technological culture often celebrates the unlimited, the boundless, the infinite. We talk about unlimited growth, about breaking all barriers, about achieving anything we can imagine. But the universe itself seems to operate differently. It has rules, constraints, boundaries. Not every imaginable thing is possible. Not every desired goal can be achieved. And perhaps there's wisdom in accepting this, in working within the universe's constraints rather than railing against them. The cosmic speed limit is the most fundamental of these constraints, at least for motion and causality. It tells us that not everywhere is accessible, that not all journeys can be completed, that patience is required for anything involving cosmic distances. This might seem limiting, frustrating, a cosmic injustice, but consider what a universe without such limits might be like. If there were no speed limit, if information could propagate instantaneously, if cause and effect could connect anywhere to anywhere without delay, the universe would be very different. It might be impossible for complexity to develop, for local structures to form, for regions to develop independently. Everything would instantly affect everything else. There would be no isolation, no independence, no opportunity for diverse developments. The cosmic speed limit creates pockets of space and time where things can happen independently, where local conditions can persist long enough for complexity to emerge. It protects developing systems from immediate disruption from distant events. It allows different regions of the universe to evolve along different paths, creating the diversity we observe in cosmic structures and potentially in life itself. In human terms, we might think of this as the value of boundaries. Just as the cosmic speed limit creates healthy boundaries between regions of space, allowing each to develop independently, personal boundaries create healthy separations between individuals, allowing each to maintain their own identity and develop in their own way. Absolute connection, if it were possible, might destroy individuality. Some separation, some limitation on how quickly and completely we can affect others is necessary for diversity and independence to exist. The acceptance of limits is also an acknowledgement of humility. We are not omnipotent. We cannot do everything we imagine. The universe has rules that constrain us, and this is not a flaw to be overcome but a feature to be accepted and worked with. There's maturity in recognizing limits, in distinguishing between what can be changed and what cannot, in directing our efforts toward the possible rather than wasting them pursuing the impossible. This doesn't mean abandoning ambition or curiosity. We should absolutely continue pushing boundaries, exploring what's possible, developing new technologies and capabilities, but we should do so with awareness that some boundaries are fundamental, that some limits are woven into the fabric of reality itself. The cosmic speed limit is one such limit. No amount of cleverness or effort will overcome it because it's not a technological barrier. It's a feature of space-time geometry. There's also something valuable in the patience that cosmic distances require. If we could travel anywhere instantly, if we could cross the galaxy in days or weeks, we might rush through exploration, might treat the universe as something to be conquered and catalogued quickly. The enforced slowness of light-speed limited travel requires us to be more thoughtful, more deliberate, more respectful of the magnitude of what we're attempting. A journey to another star that takes decades or centuries of travel time is not undertaken lightly. It requires commitment, planning, sacrifice. It requires thinking across generations, considering what we're creating for those who come after us. This long-term thinking might be valuable in itself, might teach us to consider consequences beyond our immediate lifetimes, to build things that endure. Some philosophies and traditions have long emphasized the value of working within constraints, of accepting limitations as part of the human condition. The Japanese aesthetic of wabi-sabi finds beauty in imperfection and impermanence, embraces constraints as sources of creativity. The Stoic philosophers taught acceptance of what cannot be changed, while focusing effort on what can be influenced. The cosmic speed limit fits naturally into such frameworks. Moreover, limitations often spur creativity. Artists working within the constraints of particular media or forms often produce more interesting work than those with unlimited options. Scientists working within the constraints of known physics often find ingenious solutions to problems that initially seem impossible. Constraints don't just limit, they also focus, clarify, challenge us to be more creative in working within them. The cosmic speed limit is perhaps the ultimate such constraint. It forces us to be clever about how we explore space, to think carefully about which journeys are worth the enormous investment they require, to develop technologies that maximize what's possible within the boundaries physics provides. It might ultimately lead to more thoughtful, more sustainable, more meaningful expansion into space than would occur if we could casually hop between stars. There's paradoxically a kind of freedom in accepting fundamental limits. Once you acknowledge that something is impossible, you stop wasting energy trying to achieve it. You redirect that energy toward what is possible. You find creative ways to work within constraints rather than exhausting yourself fighting against them. The cosmic speed limit, once truly accepted, frees us from unrealistic fantasies and focuses our attention on realistic possibilities. This philosophical acceptance doesn't come easily to cultures that value unlimited growth and boundless possibility, but it might be necessary for mature engagement with the universe as it actually is, rather than as we wish it to be. The universe has rules. One of those rules is that nothing exceeds the speed of light. This rule shapes what is and isn't possible, creates the structure of reality we inhabit. And in accepting this, in working within it rather than against it, we might find not limitation but a different kind of possibility. The possibility of patience, of thoughtfulness, of deep engagement with the vast cosmos that surrounds us, knowing that our exploration will be measured in generations and centuries, that our expansion will be gradual and considered, that every step beyond our world will be a momentous achievement. Which leads us naturally to the question of what it means to be human in a universe constrained by light speed, and how these physical limits might shape our understanding of our place in the cosmos. There's a beautiful connection between the cosmic speed limit and the nature of memory and history that is worth exploring as we move deeper into contemplation. When we look at distant objects in space, we're not seeing them as they are now. We're seeing them as they were in the past, when the light we're observing left them. The farther away something is, the further back in time we're looking. The cosmic speed limit thus turns the universe into a kind of memory, a record of its own history written in light. Consider the sun. It's about 8 light minutes away, which means the sunlight reaching Earth now left the sun's surface 8 minutes ago. We're not seeing the sun as it is in this moment, but as it was 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue to see it, feel its warmth, bask in its light, completely unaware that it was gone. The nearest star, Proxima Centauri, is 4.2 light-years away. We see it as it was 4.2 years ago. If a planet around that star developed intelligent life, the cosmic speed limit thus makes the universe a living archive, constantly presenting its past to anyone able to observe. and this might be another reason why the limit exists. Another feature of the universe's structure that has value beyond mere constraint. A universe without a speed limit might lose its history, might exist only in the present with no accessible record of what came before. The light speed limit ensures that the past remains visible, that history endures in the form of photons still in transit. For beings like us who exist in time, who value history and memory, who learn from the past and navigate the future, this cosmic preservation of history through the speed limit might be essential. We can literally see our cosmic origins, can observe the early universe, can study the history of galaxies and stars not through inference, but through direct observation. The past isn't lost. It's constantly arriving, constantly accessible, constantly teaching us about where we came from and how we got here. And so, the cosmic speed limit, which seems at first like merely a frustrating constraint on how fast we can travel, reveals itself as something deeper, a fundamental feature of how the universe remembers, how it preserves and presents its history, how it connects past and present through the medium of light. The universe doesn't forget. It remembers in light, and the cosmic speed limit ensures that this memory endures. Let's carry this contemplative mood forward as we consider what all of this means for our deepest questions about existence and our place within it. As we enter the final phase of our journey together, let's contemplate something that might seem paradoxical. The cosmic speed limit, which has seemed throughout this exploration like a limitation, a boundary, a frustration, is actually part of what makes the universe comprehensible, beautiful, and mathematically elegant. The same laws that prevent us from travelling faster than light also ensure that the universe is logically consistent, that it follows rules we can understand and predict. The beauty of physical law lies in its universality. The same equations that describe an apple falling from a tree describe the motion of planets around stars. The same principles that govern atoms also govern galaxies. The speed of light appears in equations across all domains of physics, connecting phenomena that seem unrelated. It's in Maxwell's equations of electromagnetism, in Einstein's energy-mass relation, in the Lorentz transformations that describe how space and time change with motion. This interconnectedness suggests something profound. The universe is not a collection of arbitrary rules, but a unified system where deep principles shape everything. The cosmic speed limit isn't an isolated fact, but a consequence of how space-time is structured, which in turn affects everything from the behaviour of particles to the evolution of galaxies. Pull on one thread of physical law, and you find it's connected to all the others. There's something almost musical about this. Just as a symphony has themes that recur and interweave, developing and transforming throughout the piece, physical law has fundamental constants and principles that appear everywhere, connecting seemingly disparate phenomena. The speed of light is one of these fundamental constants, a number that appears again and again, that links electricity to magnetism, mass to energy, space to time. This mathematical elegance is not something humans imposed on nature. We discovered it, found it already present in how the universe operates. The equations we write are our attempts to capture patterns that exist independently of us, and those patterns have a beauty and consistency that suggests something deeper than random chance. Though what that something might be remains open to interpretation and wonder. Consider how different the universe would be if the cosmic speed limit didn't exist, or if it were different. Without a maximum speed for causation, without the connection between space and time that the speed of light provides, the equations of physics would be very different, perhaps impossibly complex or inconsistent. The fact that they work, that they're elegant and predictive, that they describe our universe so accurately, might depend on this fundamental constraint. In mathematics, constraints often lead to elegance. A mathematical problem that's too unconstrained, too free, might have no interesting solution or infinitely many trivial solutions. Add the right constraints, and suddenly there's a unique, beautiful solution. one that satisfies all the conditions in a way that seems almost inevitable. The cosmic speed limit might be playing a similar role in the mathematics of physics, constraining the possible in ways that lead to elegant, consistent laws, and these laws are accessible to us. We can understand them, can write them down in equations, can use them to predict how the universe will behave, a human mind. A particular arrangement of atoms that emerged through evolution on a small planet can comprehend the fundamental rules governing all of reality. That's remarkable. It suggests that the universe is not only lawful but comprehensible, that intelligence and physical law are somehow matched to each other. Perhaps this comprehensibility is another consequence of the cosmic speed limit. Because causation propagates at a finite rate, because local regions can maintain coherence, patterns can emerge and persist long enough for complexity to develop. And that complexity can become intelligent, can begin to understand the very laws that allowed its existence. The cosmic speed limit creates the conditions for this understanding to be possible. There's also beauty in the specific value of the speed of light. 300,000 kilometers per second seems arbitrary, but when you express it in natural units, relating it to other fundamental constants, it has a kind of inevitability. In systems where we set certain constants to 1, the speed of light often becomes simply the unit ratio between space and time. It's not that light travels at this speed, but that this is the natural conversion factor between spatial and temporal dimensions. This suggests that the speed of light is less like a speed limit on a highway, arbitrarily set by some authority, and more like a fundamental feature of geometry itself. In the geometry of space-time, the speed of light is the rate at which space and time exchange. It's built into the structure of reality at the deepest level we can currently access, not added on top but woven throughout. And when we study the history of physics, we find that understanding this cosmic speed limit led to some of the most profound insights we have achieved. Relativity revolutionized our understanding of space, time, matter, and energy. Quantum field theory, which unites quantum mechanics with relativity, gave us our deepest understanding of particles and forces. Cosmology, which applies these theories to the universe as a whole, has revealed the history and structure of the cosmos itself. All of these achievements came from taking the cosmic speed limit seriously, from accepting it as a fundamental feature of reality and exploring its implications. The limitation became a doorway to deeper understanding. What seemed like a boundary to our ambitions turned out to be a pathway to knowledge, a thread that when followed led to some of the most beautiful insights in the history of human thought. So the cosmic speed limit, which we've been examining throughout this journey as something that constrains us, that limits what we can do and where we can go, is simultaneously the source of some of our deepest understanding. It's a key that unlocks mysteries, a constraint that generates elegance, a limitation that points toward truth. And recognizing this dual nature, the way that boundaries can enlighten even as they constrain, might help us appreciate the cosmic speed limit not as an enemy to our ambitions, but as a teacher revealing the structure of reality, which leads us to consider what role light itself plays in this elegant system, and why the boundary between light and matter is so fundamental. Throughout this exploration, we focused on light speed as a barrier, a limit, something we cannot exceed. But let's shift perspective now and consider what light does rather than what it prevents. Light is the primary way the universe communicates with itself, the messenger that carries information from place to place, the medium through which distant events become knowable to us. Understanding light's role helps us appreciate why its speed is so fundamental. Everything we know about the universe beyond our immediate reach, we know because of light. The sun's warmth, the moon's glow, the stars scattered across the night sky, the distant galaxies revealed by telescopes, all reach us through photons, through light travelling across space. When you look at something, you're detecting photons that bounced off it or were emitted by it. Vision itself is the detection of light, and through vision we construct our understanding of the world around us. But light carries more than just images. Encoded in a photon's energy is information about what created it, about the temperature and composition of its source, about how fast that source was moving, about what it passed through on its journey. Astronomers can analyze starlight and determine that star's temperature, its chemical composition, whether it has planets, how fast it's rotating, whether it's moving toward or away from us. All of this information is carried by light. The photons reaching us from the Andromeda Galaxy left that galaxy 2.5 million years ago, when our ancestors were just beginning to make stone tools. Those photons have been travelling through space all that time, maintaining the information they carry, delivering it faithfully across the cosmic void. They tell us about a galaxy and its past, show us its structure and composition, let us study something impossibly distant through the messenger of light. And light is perfectly suited to this role. Photons don't decay. They don't change their properties during travel unless they interact with something. A photon emitted billions of years ago, and billions of light years away, can reach us essentially unchanged, can deliver information about the ancient universe with remarkable fidelity. Light is a stable, reliable messenger, preserving what it carries across immense distances and times. Moreover, light carries information efficiently. A single photon encodes data in its energy, its polarization, its direction, and we can detect individual photons with appropriate instruments, can extract information from each one. Modern detectors are so sensitive they can register single photons arriving from distant stars, can count them one by one, can analyze their properties individually. This makes light an information channel of remarkable capability. The cosmic speed limit is intimately tied to light's role as messenger. Because light travels at the maximum possible speed, information propagates as fast as physics allows. Any physical process that carries information, from radio waves to particle beams to gravitational waves, travels at light speed or slower. Light sets the pace for how fast the universe can communicate with itself. This creates an interesting situation where the fastest possible communication is still limited, still finite. Justice still requires time. There is no instantaneous communication across distance in our universe. Information must travel, must cross space at a finite rate, must take time proportional to distance to reach its destination. This delay is fundamental, built into the structure of space-time, unavoidable. And perhaps this delay serves a purpose. It means that different regions of space have some independence, some isolation from each other. Events here don't instantly affect events there. There's time for local coherence, for patterns to develop, for complexity to emerge without immediate disruption from distant influences. The finite speed of light creates a kind of buffering, a temporal spacing that allows the universe to be structured rather than homogeneous. When we communicate across human distances, light speed seems instantaneous. A phone call across the country involves signals travelling at light speed through fibre optic cables, but the delay is only milliseconds, imperceptible to our conversation. Light has time to travel around Earth 7.5 times in a single second. At human scales, light speed is effectively infinite. But on cosmic scales, light's finite speed becomes significant. Communicating with a Mars rover involves delays of several minutes as radio signals cross the space between planets. Communicating with a probe near Neptune involves hours of delay, and communicating across light years would involve delays of years or decades, transforming communication from dialogue to correspondence, from conversation to historical exchange. This scaling is elegant. Light is fast enough to make local communication effectively instantaneous, allowing complexity and life to function, allowing consciousness to integrate information from our surroundings rapidly enough to navigate and survive. But light is slow enough on cosmic scales to create isolation, to prevent instant universal connection, to give different regions of the universe some independence. And light connects not just space but time. When we observe distant galaxies, we're literally seeing the past. The light carries information from then to now, bridges temporal as well as spatial gaps. Every observation of something distant is simultaneously an observation of something ancient. Light makes the past visible, preserves history, allows us to study the evolution of the universe by looking at objects at different distances and thus different times. There's something beautiful about this dual role. Light is both the fastest thing in the universe and the primary carrier of information. It sets the ultimate speed limit while simultaneously being the messenger that connects everything. It's the medium through which the universe becomes knowable, through which distant reaches of space and time become accessible to observation and study. And we, as beings who can see, who can detect and analyze light, are participants in this cosmic communication network. Every time we look at the stars, we're receiving messages sent long ago by distant suns. Every time we point a telescope at a galaxy, we're accessing information from the deep past. We're reading the universe's history, delivered to us by light, travelling at the cosmic speed limit, faithfully carrying its message across the void. So light is not just a phenomenon to study or a speed limit to contemplate. It's the medium of cosmic connection, the messenger that makes the universe comprehensible, the carrier of information that allows anything to know anything about anything else. And the cosmic speed limit is the speed of this knowing, the rate at which understanding can propagate through space, the pace at which the universe reveals itself. From this perspective on light as messenger, let's turn to consider what it means to observe, to see, to know, in a universe where information travels at light speed. We've discussed throughout this journey that we cannot know the current state of distant objects because light takes time to reach us. But there's something deeper here worth contemplating. The very nature of observation, of knowledge, of what it means to know something about the universe when all our knowledge comes through light speed limited signals. In our everyday experience, we tend to think of observation as instantaneous, as giving us information about the current state of things. You look at a tree and see the tree as it is now. But even that isn't quite true. Light takes time to travel from the tree to your eye, a tiny fraction of a nanosecond for something a few meters away. Your brain takes additional time to process that light, to construct the image you perceive. By the time you consciously register seeing the tree, you're seeing it as it was in the very recent past, milliseconds ago. This delay is negligible for everyday purposes. The tree doesn't change significantly in nanoseconds or milliseconds. But the principle is important. All observation is observation of the past. We never truly see anything as it is in the present moment. We always see things as they were when the light we're detecting left them. On cosmic scales, this becomes profound. We see the sun as it was 8 minutes ago. We see the nearest stars as they were years ago. We see distant galaxies as they were billions of years ago. Our entire picture of the universe is a picture of its past, a collage of different paths depending on distance. The universe we observe exists only in memory, in light that has been travelling toward us, in information that is just now arriving. This raises interesting philosophical questions. What does it mean for something to exist if we can never observe it in its present state? Is the Andromeda Galaxy as it is right now part of our universe, even though we cannot observe it, can never know its current state? Or is our universe limited to what we can observe, to the information that has had time to reach us? Physics tends to answer this through the concept of the observable universe, the region of space from which light has had time to reach us since the Big Bang. Beyond this region might lie more universe, perhaps infinite in extent, but it's not part of our observable universe because its light hasn't reached us yet. In a very real sense, the unobservable universe doesn't exist for us. We cannot interact with it, cannot know anything about it, cannot be affected by it or affect it. So our reality, the universe we inhabit, is fundamentally limited by the cosmic speed limit. It's the bubble of space from which information travelling at light speed has had time to reach us. This bubble is centred on us, on Earth, and it grows at the speed of light as time passes. Every second, light from regions slightly farther away reaches us for the first time, very slightly expanding our observable universe. But there's a complication. The universe is expanding and the expansion is accelerating. There exist regions of space that are receding from us faster than light due to the expansion of space itself. Light from these regions will never reach us, no matter how long we wait. These regions are beyond our cosmic horizon, permanently unobservable, forever outside our reality in any practical sense. This means there's a fundamental limit to what we can know about the universe. Not just a practical limit based on current technology, but a fundamental limit based on the structure of space-time. Some things are unknowable because information about them cannot reach us, will never reach us, is prevented from reaching us by the combination of the cosmic speed limit and cosmic expansion. And yet, within our observable universe, within the bubble of space from which information can reach us, we can know an enormous amount. We can study galaxies billions of light years away, can analyze their light, can determine their composition and motion and history. We can observe the cosmic microwave background radiation, light from when the universe was only 380,000 years old, and extract from it information about the universe's composition, geometry, and evolution. The cosmic speed limit, rather than preventing knowledge, actually makes certain kinds of knowledge possible, because light from different distances takes different amounts of time to reach us. We can observe the universe at different ages simply by looking at different distances. The universe shows us its entire history, from the early universe billions of years ago to relatively recent events millions of years ago to the near present of our own galaxy. Without the cosmic speed limit, without the finite speed of light, this wouldn't work. If information propagated instantaneously, we'd see everything as it is right now, would lose access to the past. The time delay created by light's finite speed is what allows us to observe cosmic history, to study the evolution of the universe, to understand where we came from. So the limitation becomes enabling, the constraint creates possibility. What seems at first like a frustrating barrier to knowledge turns out to be what makes certain deep knowledge accessible. We can know about the early universe precisely because light from the early universe is just now reaching us, having travelled for billions of years to deliver its message about the cosmos's youth. There's also something profound about the fact that observation requires interaction. To see something, photons must travel from it to your eye or detector. This means every observation is a physical process, an exchange of energy and information, a causal connection between observed and observer. You cannot observe without interacting, cannot know without being physically connected through light. This gives knowledge a physical character. Knowing something about a distant star requires photons from that star to reach you, to interact with your instruments or your eyes, to deposit their energy and information. Knowledge is not abstract but physical, mediated by real particles travelling through real space, carrying real information that can be detected and analysed. And the cosmic speed limit governs all of this. It determines how fast information can travel, how quickly we can learn about distant events, how much we can know about the current state of the universe. It creates the structure of our knowledge, the pattern of what is and isn't accessible, the boundaries of what can be observed and understood. We are, each of us, observers in a light-speed limited universe, beings who can know only what light has had time to show us, who construct our understanding of reality from information that has travelled to us across space and time. Our picture of the universe is necessarily incomplete, limited, shaped by the cosmic speed limit. But within those limits, we can know deeply, can understand profoundly, can extract from the light that reaches us a comprehensive picture of cosmic history and structure. And perhaps that's enough. Perhaps the limitations on what we can know, imposed by the cosmic speed limit, actually make our knowledge more precious, more hard-won, more meaningful. We cannot know everything, but we can know much. We cannot observe the present, but we can study the past. We cannot reach most of the universe, but we can understand much of what we can observe. The cosmic speed limit shapes not just what we can do, but what we can know. And in shaping the boundaries of knowledge, it also shapes the meaning of understanding, the value of discovery, the significance of every photon that reaches us carrying information from the depths of space and time. Let's move now towards something simpler and more fundamental. The sheer fact of light existing, of photons travelling through space, of the universe being visible at all. We've explored complex physics, contemplated philosophical implications, examined mathematical relationships. But as we near the end of our journey together, let's return to something simpler and perhaps more profound. The basic, undeniable wonder of light itself, of photons travelling through space, of the universe being illuminated and knowable. Consider a single photon emitted from a distant star. It emerges from nuclear fusion deep in that star's core, energy created by hydrogen atoms fusing into helium, releasing light. That photon, or rather the energy that will become that photon, takes thousands of years to random walk its way from the core to the star's surface, bouncing and being absorbed and re-emitted countless times in its journey through the dense stellar interior. But finally it reaches the surface, breaks free from the star's gravity, and begins its true journey through space. Outward it travels at 300,000 kilometers per second, maintaining its direction and energy, neither speeding up nor slowing down, crossing the vast emptiness between stars. For years or decades or centuries or millennia, depending on the distance, that photon travels through darkness, through vacuum alone. And then, after all that time, after crossing distances so vast that human minds struggle to comprehend them, that photon encounters Earth. It passes through our atmosphere, perhaps refracting slightly through air, perhaps scattering off molecules, and it strikes something, perhaps the mirror of a telescope, perhaps directly into someone's eye. After its immense journey, it deposits its tiny amount of energy, delivers the information it has carried across the cosmic void, and ceases to exist as a photon. But in that moment of arrival and absorption, something remarkable happens. That photon's information becomes knowledge. We see the star. We learn about something distant, something we could never touch or visit, something that might not even exist anymore by the time its light reaches us. We connect across the void, across time, through the messenger of light. Every time you look at the night sky, this is happening. Countless photons from countless stars are completing journeys that began years or decades or centuries ago. Each photon carries information, tells a story, connects you to something distant and ancient. Your eyes or your telescope collects these photons, gathers the information they carry, and from this assemblage of ancient light, you construct an image of the universe. There's something profoundly beautiful about this process. The universe makes itself knowable through light. Stars don't just exist in isolation. They emit photons, send information into space, make themselves visible to any observer who can detect their light. The universe is not silent and dark and unknowable. It's luminous, communicative, constantly broadcasting its presence through light travelling in all directions. And light itself, what is it? Quantum mechanics tells us it's both wave and particle, electromagnetic radiation that exhibits properties of both. It's packets of oscillating electric and magnetic fields, mutually generating each other, propagating through space. It's photons, quantum particles with energy but no mass, travelling at the cosmic speed limit because they must, incapable of any other velocity. But beyond the physics, there's the simple experiential fact of light. Light is what makes vision possible, what allows colours to exist for us, what enables us to perceive the world around us. Light is what creates shadows and illumination, what makes photography possible, what powers plants through photosynthesis, what warms Earth and makes life possible. The sun's light has been travelling for 8 minutes when it reaches Earth. But in those 8 minutes, it crosses 150 million kilometres of space, delivering energy that drives our entire biosphere. Plants capture that light, use its energy to build complex molecules from simple ingredients. Animals eat plants, or eat other animals that ate plants, living on energy that originated in the sun and was delivered by photons crossing the void. In a very real sense, we are creatures of light. The food we eat, the oxygen we breathe, the warmth that keeps our planet habitable, all ultimately trace back to sunlight. We evolved on a planet bathed in light from a nearby star, adapted to use that light for vision, developed civilizations that harness light for communication and knowledge and art. And now, with modern technology, we can detect light far dimmer than our eyes can see, can analyze its properties in exquisite detail, can extract from starlight information our ancestors never imagined. We can split light into spectra, seeing the rainbow of colours it contains and the dark lines where specific wavelengths are absorbed. From these patterns we deduce the chemical composition of stars, the temperature of their surfaces, the speed of their rotation and orbital motion. We can detect light from the cosmic microwave background, photons that have been travelling for nearly 14 billion years, light from when the universe was young and hot and filled with glowing plasma. These ancient photons tell us about the universe's birth, its early evolution, its ultimate fate. Light from the very beginning of observable time reaches us still, carries information about the cosmos's origin. There's something almost miraculous about this accessibility. The universe doesn't hide its secrets. It broadcasts them in light, makes them available to anyone with the means to observe. Distant galaxies announce their presence through the photons they emit. Ancient events remain visible through the light still travelling from them. The cosmos is an open book, written in light, readable to those who learn its language. And the cosmic speed limit is what makes this possible. Light travels fast enough to reach us from anywhere in the observable universe, given sufficient time. Light is stable enough to carry information faithfully across billions of years and billions of light years. Light is interactive enough to be detected, to deposit its energy, to make itself known. The universe, through light travelling at its characteristic cosmic speed, makes itself comprehensible. When you look at the stars tonight, if the sky is clear wherever you are, take a moment to think about this. Those points of light are messages from distant suns, photons that have travelled for years to reach your eyes, information about places too distant to ever visit but knowable through the light they emit. You're seeing across space and time, connecting to the universe through the fundamental messenger of light. And in seeing, in observing, in knowing, you're participating in one of the universe's most fundamental processes, the propagation of information through light, the connection of distant places through photons travelling at the cosmic speed limit, the transformation of ancient light into present knowledge. You're an observer in a luminous universe, a being capable of detecting light, of extracting meaning from photons, of understanding the cosmos through the information light delivers. The cosmic speed limit is not just a constraint on motion, but the speed of illumination, the rate at which the universe reveals itself, the velocity of understanding. And in accepting this speed, in working within it rather than railing against it, we connect to something fundamental about how reality operates, how knowledge propagates, how the universe communicates with itself and with us. Let's carry this sense of wonder and acceptance into our final chapter, where we'll synthesize everything we've explored and find peace in understanding. We've journeyed far together through concepts and implications, through physics and philosophy, through mathematics and meaning. We've examined the cosmic speed limit from every angle we could imagine, understood why it exists, explored what it prevents and what it enables. As we approach the end of our time together tonight, let's synthesize all of this into a final contemplation. What it means to live, to exist, to be conscious in a universe with this fundamental limit. The cosmic speed limit is woven into the deepest structures of reality we can access. It's in the equations that describe space-time, in the principles that govern causality, in the relationships between energy and mass space and time, information and observation. It's not arbitrary or accidental, but fundamental, as basic to the universe as the existence of space and time themselves. And because it's fundamental, because it's woven into reality at the deepest level, it shapes everything. It determines what is and isn't possible, what can and cannot happen, what we can and cannot do. It creates the structure of our existence, the boundaries within which we must operate, the constraints we must accept. But constraints are not necessarily limitations in a negative sense. They're structure, guidance, the rules that make the game playable. A universe without constraints, without fundamental laws, would be chaos, formless, perhaps incapable of supporting complexity or life or consciousness. The cosmic speed limit is one of the constraints that makes our universe the ordered, comprehensible, livable place it is. Living within this constraint means accepting that some things we can imagine are impossible. We cannot visit distant galaxies within human lifetimes. We cannot know the current state of anything beyond our local cosmic neighbourhood. We cannot break the fundamental connection between space and time, cannot escape the arrow of causality, cannot exceed the speed at which information propagates through the universe. These limitations might seem frustrating when we first confront them. Our dreams are bigger than what physics allows. Our imaginations can conceive of faster-than-light travel, of instant communication across cosmic distances, of empires spanning galaxies. Science fiction has painted vivid pictures of such possibilities, has made them seem almost within reach. But reality is not science fiction. And the universe operates according to its own laws, not our preferences. And there's maturity in accepting this, in distinguishing between what we can imagine and what is actually possible, in focusing our efforts and dreams on what physics allows, rather than wasting them on what it forbids. Within the cosmic speed limit, within the constraints physics imposes, there remains vast possibility. We can explore our solar system, can potentially establish human presence on other worlds in our stellar neighbourhood, can study the entire observable universe through telescopes, can gradually expand our civilization across the reachable cosmos. The limitations are real, but so are the possibilities, and perhaps the limitations themselves have value. Perhaps the isolation created by the cosmic speed limit protects us, gives us time and space to develop without interference, allows diversity to flourish across the galaxy. Perhaps the patience required for interstellar travel teaches us to think across generations, to build for the long term, to create legacies that endure. Perhaps the wonder of observing distant galaxies is enhanced by knowing we can never visit them, that their beauty must be appreciated from afar. There's a kind of peace in accepting fundamental limits. Once you truly understand that something is impossible, you stop wasting energy fighting it. You redirect that energy toward what is possible. You find creative ways to work within constraints rather than exhausting yourself against them. You discover that boundaries can clarify rather than merely limit, can focus attention on what matters most. The cosmic speed limit clarifies what matters. It matters that we understand our local universe, our solar system, our planet. It matters that we develop sustainable ways of existing in space, technologies that can support us for the long journeys interstellar travel requires. It matters that we think across generations, that we create things that endure beyond our individual lifetimes. It matters that we appreciate beauty and wonder in the cosmos around us, that we study and understand and marvel at the universe we can observe. What doesn't matter, what we can let go of, are the impossible fantasies. We will never casually hop between galaxies. We will never build instantaneous communication networks spanning the universe. We will never exceed the cosmic speed limit. And that's okay. The universe has its structure, its rules, its fundamental nature. Our role is not to break those rules, but to understand them, to work within them, to find meaning and purpose in the reality that actually exists rather than the fantasy we might prefer. And there's profound meaning to be found in a universe with a cosmic speed limit. Every photon that reaches us is a messenger from across space and time. Every observation of a distant star connects us to something ancient and far away. Every discovery about the universe's structure reveals new aspects of the elegant laws that govern reality. Every challenge the cosmic speed limit presents invites creativity and ingenuity in finding solutions. We are beings of consciousness and intelligence, arising through natural processes on a small planet, capable of understanding the fundamental laws that govern all of reality. We can look at the stars and comprehend what we're seeing, can decode the messages carried by light, can understand why the universe has a cosmic speed limit and what that limit means. This capability, this understanding, is itself remarkable, perhaps even miraculous. And the cosmic speed limit, rather than being an enemy to this understanding, is part of what makes it possible. The structure of space-time, the relationship between space and time encoded in the speed of light, the propagation of information at a finite rate, all of these create the conditions for complexity, for life, for consciousness. We exist because the universe has these particular laws, including the cosmic speed limit. So perhaps the right response to the cosmic speed limit is not frustration but gratitude. Not disappointment at what we cannot do, but appreciation for what we can. Not rebellion against fundamental law, but acceptance of the elegant structure of reality. The universe is not obligated to fulfill our fantasies. It is what it is, governed by the laws that make it stable and comprehensible, and capable of supporting beings like us who can study it and understand it and find meaning in it. Living within the light, living in a universe with a cosmic speed limit, means accepting our place in this structured reality. It means being patient with the vastness of space and time, being creative within the constraints physics imposes, being grateful for the understanding we can achieve, being content with observing what we cannot reach, being committed to gradual expansion rather than instant conquest. It means looking at the stars with wonder, knowing that the light reaching our eyes carries information from distant places and ancient times, that we're connected to the universe through this fundamental messenger travelling at the cosmic speed limit. It means appreciating the beauty of physical law, the elegance of equations that describe reality, the deep structure that makes the universe comprehensible. It means finding peace in understanding, in accepting, in working within rather than against the fundamental nature of reality. The cosmic speed limit is not a failure of the universe to meet our expectations. It's a feature of how the universe actually is, how space-time is structured, how causality propagates, how information flows. And in accepting this, in truly understanding it, we connect more deeply to the cosmos we inhabit. The universe is vast beyond imagination, ancient beyond comprehension, governed by laws we can understand, limited by constraints that create structure and possibility. We exist within it, small but conscious, limited but capable, bound by cosmic law but free within those bounds to explore, to discover, to wonder, to find meaning in our brief existence under the light of distant stars, forever travelling at the cosmic speed limit, forever bringing us messages from the depths of space and time, forever reminding us of the beautiful, elegant, constrained universe we call home. And so we've travelled together, you and I, through nearly 2.5 hours, exploring why light-speed travel is impossible, and what that means for our understanding of the universe and our place within it. From Einstein's revolutionary insights to the vast distances between stars, from the mathematics of space-time to the philosophy of limits, from the practical challenges of interstellar travel to the simple wonder of light itself, we've covered vast conceptual territory. Trying always to move slowly, to breathe, to let understanding settle naturally. We began with the mystery of light's constant speed, that strange experimental result that revealed space-time as a unified fabric. We explored how mass and energy are related, how time dilates and space contracts at high velocities, how approaching light speed creates insurmountable barriers. We contemplated causality and cosmic horizons, the isolation that the speed limit creates, the ways it protects diversity and allows complexity to develop. We examined quantum mechanics and general relativity, both of which respect the cosmic speed limit in their own ways. We considered what existence is like for photons travelling at light speed, timeless and spaceless, connecting the universe without experiencing the journey. We looked at the Fermi paradox through the lens of cosmic isolation, at humanity's realistic future among the stars, at the patience and perspective required for interstellar exploration. And we moved gradually into more contemplative territory, considering the elegance of physical law, the role of light as cosmic messenger, the nature of observation and knowledge, the simple wonder of photons crossing darkness to reach us. We reflected on what it means to live in a universe. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. We reflected on what it means to live in a universe with fundamental limits, to accept constraints as structure rather than mere limitation, to find meaning within the boundaries reality imposes. The answer, as honestly as I can give it, to the question of why light-speed travel is impossible, because the universe is structured in a very particular way, with space and time unified into spacetime, with causality propagating at a maximum rate, with mass and energy related such that infinite energy would be required to accelerate any massive object to light speed. It's not a technological limitation, but a fundamental feature of reality itself, woven into the deepest laws we know. And perhaps the deeper answer is that the universe doesn't need to allow faster than light travel, that the cosmic speed limit creates the kind of universe where complexity and life and consciousness can develop, where information can propagate and create structure, where different regions can evolve independently, where knowledge comes from observation of light carrying messages from across space and time. If you enjoyed this slow drift through cosmic physics and philosophical contemplation, a like and subscribe helps others find these peaceful explorations of the universe's deepest mysteries, and please share your thoughts in the comments. Where in the world are you listening from? What aspect of the cosmic speed limit fascinates you most? What questions remain? I read every comment, and your reflections often inspire future journeys like this one. To those already part of this community, thank you for being here, for travelling with me through these long, nocturnal contemplations of space and time. Wherever you are in the world right now, whether it's late at night or early morning, whether you're in darkness or daylight, I hope you found some peace in understanding, some acceptance of the beautiful limits that structure our universe. I hope your breathing has slowed, your thoughts have settled, your body has grown heavy with approaching sleep. I hope the cosmic speed limit seems less like a frustration and more like an elegant feature of reality. A boundary that creates possibility even as it constrains. Look up at the stars if you can, or picture them if the sky's clouded. Those points of light are photons reaching you after journeys of years or decades, messages from distant suns, information travelling at the cosmic speed limit. Each photon that reaches your eyes has crossed vast distances at 300,000 kilometers per second, neither faster nor slower, maintaining its direction and energy, delivering its message about a distant place in ancient time. All those stars, all those galaxies, all that light crossing the darkness, all of it governed by the same elegant laws, all of it limited by the same cosmic speed limit. And here you are, a conscious being on a small planet, able to detect that light, to understand what it means, to comprehend the deep structure of space-time that makes the universe both vast and knowable, both limited and full of possibility. The cosmic speed limit is not a failure but a feature, not a barrier but a structure, not a denial but a guide. It shapes what is and isn't possible, creates the universe we inhabit, enables the complexity that makes our existence possible. And in understanding it, in accepting it, in finding peace with it, we connect more deeply to the reality we're part of, to the elegant laws that govern all things, to the beautiful, limited, luminous cosmos we call home. Sleep well tonight, under stars whose light has travelled for years to reach you, in a universe structured by the cosmic speed limit, knowing that some journeys take lifetimes, that some things are impossible, that some beauty can only be appreciated from afar. Dream, if you will, of distant galaxies and ancient light, of photons crossing the void, of the patient unfolding of cosmic time, of your place in a vast and elegant universe. Good night.